Hi, this is Mr. Manley. In this video, we're going to find the value, the trig value of an angle that is not on a unit circle. It's on a more general trig circle that does not have a radius of 1. So you may notice that when we talk about the XYR definition of a trigonometric function, we would say y over r. And initially we're working on the unit circle, and r is always dropping out because r is 1. And you may have asked yourself, well, why do we even have r? Why don't we just say sine theta is equal to y? And that's because we can have a trig circle that does not have a radius of r. And this problem presents just such a case. So here we're given the terminal side of an angle, terminal side of theta, and it passes through the circle at 0.54. So I'm going to take an angle here and I'm going to rotate through, and I want to go somewhere where the x value is going to be a little bit longer than the y value. Like up here, the y value is bigger than the x value, right? If I'm just looking at where the angle, the red bar segment, is intersecting the circle. So I want to go somewhere like maybe around here where I feel like the x value is a little bit longer than the y value. So that might make sense for me to say that this point here, this point right here is 0.54. And the question is, what is the sine of that angle? Well, what are ways that we have found the sines of angles? So, I mean, we had right triangle trigonometry, so we're able to do opposite over hypotenuse. We had a calculator, of course. You're just going to punch in the sine, and you're going to punch in the angle. But here we don't have the angle. We have this information about it, but we don't know what the actual angle is. And then another thing that we had is the unit circle. But the unit circle is very specific about when we can use it. We can use it when it is a multiple of 30 degrees, 45 degrees, 60 degrees, or 90 degrees, or, of course, the radian equivalence. So we don't have any of that here. What we have is 0.54, and we know that sine of theta is equal to y over r. So, for instance, up to this point, at this point, without giving you further instruction, hopefully you'd be able to at least get a start and say, well, the sine of theta is equal to 5 over something, and you might be lost in your understanding of the things and just say, well, r is always 1. But not in this case. R is not 1. So at this point, we know 5 over r, and what is r? Well, let's look at our picture for one. In this picture here, this side is the length of x, which is 5. This side is the length of y, which is 4. And you can see the way I've drawn it there that there's a right angle. So how about Pythagorean theorem to find out what r is? There's r, and the Pythagorean theorem says that 5 squared plus 4 squared is equal to r squared. And we can find out what r is. So I've got 25 plus 16, which is 41, equals r squared. And of course, I can square root both sides, and I get r is rad 41. Now I've got r. So square root of 41. And there's no stipulation here about rationalizing the denominator. We're not expressing this as an approximation and rounding off to the nearest tenth or the nearest hundredth. So really, I should be able to enter my response like that, 5 over rad 41. Let's look at cosecant. What's the cosecant of theta? Cosecant theta is r over y. I know what r is, rad 41. I know what y is, 4. So it's rad 41 over 4. And I made an error back here, didn't I? You were probably shouting, some of you were probably shouting at your screens a minute and a half ago or so. Sine theta is y over r, and for some reason I put a 5. But yeah, the y coordinate is 4. And then the r, of course, is rad 41. So that's going to be this. That's what I want there, not the 5. So sorry if you were pulling your hair out there for a moment. Let me replace that and call this 4 over rad 41. Just a comment, the reason that caught my eye probably is because I know that cosecant is the reciprocal of sine. So as I was doing cosecant here and noticing that those were not matching up, that really drew my attention to it. So always good to be having some sort of check of your work. Always keeping sense of what should be happening so that we can catch little errors like that. Okay, let's go to cotangent theta. And that's equal to x over y. And I got the information, I was given the information in the first line, right? The x coordinate is 5, and the y coordinate is 4, and it's as simple as all that. So here we have a trig circle, or an angle that is on it, that we place on a trig circle that does not have a radius of 1. And the way that we identify what the radius is always going to be, we're always going to be able to use the Pythagorean theorem. I'll just show you one more thing. What if I had an angle with a terminal side that ended up in this quadrant over here? And then I would have to know something about this point, and I'll just make something up here that's like point negative 4, 2, let's call it. So I've got the x, I've got the y, and where's the r coming from? We just build our little right triangle here. Right triangle, x. So I've got, if I'm thinking about this as a triangle, I'm really not going to talk about that side as negative 4, because I don't think about the lengths of sides of a triangle having a negative value. So I'm actually just going to say, I'm just going to write a 4 down there. So I've got that side is 4, this side is 2, and then we can find r using the Pythagorean theorem. So you see that it doesn't matter where we are. Just one final thing. I think it's perfect to think about this as a Pythagorean theorem application, but we could also have this general formula that is out there, that in these trig circles in trigonometry, and we're working on a trig circle on an xy axis, that we can always say that x squared plus y squared is equal to r squared.